Now we'll look into how data is accessed from the data segment. The program makes three data declarations in this data segment. X and Y can be thought of as labels that point out to two distinct 4-byte locations or word-sized locations in the memory and initialized to 5 and 3. Z points out at two word structures in the memory and is not initialized to anything. So if a block represents a word, then this is how the data layout will look in the memory. Data can be accessed through its location in the memory. Here, the base address of X is loaded into register T0 using the load address instruction, and then the 4 bytes contents of this location are loaded into register T1 using the load word instruction. Or you could simply use the pseudo instruction of this format, which performs both operations implicitly. Now suppose that we add X and Y and want to store the sum and the value of Y in the two 4 bytes location available for use at Z. In this example, what we do is that by loading the base address of Z in register T4 and then specifying the byte offset in the store word instruction, since the space reserved at Z is 2 words, the byte offset specified for the first word is 0, while the offset for the second word is 4. And as a result of executing these instructions, we can see that 8 is stored at the first word at Z and 3 is stored at the second word at Z. Now we'll consider accessing arrays. Generally speaking, arrays can be formed for different data types such as bytes, words, and double words. In this example, we consider accessing an array of words. So you see that the data type word has been specified for this array in the data segment. So what we do is that we start off by declaring an array of 10 words with each word initialized with a value between 1 and 10. In the memory, this will appear as a contiguous region of words initialized to the corresponding value. The contents of the array can be accessed first by first loading the base address of the array, which in this case happens to be this hexadecimal number. And this address is actually used in the load address instruction at that point. That's actually the first instruction in the main. Now the contents of the array can be loaded by specifying the right offset. Since it is an array of words and each element in the array is spaced at regular offsets of 4 bytes, the offset to all elements will always be a multiple of 4. So what we can do is that we can actually use this property to access such an array inside a loop, provided that the size of the array is known beforehand. In this example, we have an array of 10 words that has been declared and initialized in the data segment. So that's the array of words. And the variable size is set to 10. So the variable size is set to 10, and that gives us the size of the array. So how can you write a loop that would go through all the elements inside the array? You can think of a for loop as an example. To begin with, we need an index I to keep track of how many elements in the array have already been accessed. So what we do is that we keep the index I in the register T0 and we initialize that to 0. We will increment it at the end of each iteration. Next, we load the size of the array to keep checking if we have reached the end of the array after each iteration. We would also need the base address of the array. Remember from the previous slide that we added an offset to the base address of the array to get the right element. Also remember that it is an array of words, so the offset will always be a multiple of 4. What we do is that we calculate this offset with this instruction, and that's by multiplying the index that is stored in T0 by 4. So this is what this instruction does is basically it shifts the index that is stored in T0 by 2 bits to the left, and that is equivalent to multiplying it by 4. Now remember that shifting left once is equivalent to multiplying by 2. So shifting left twice naturally implies that it's equivalent to multiplying by 4. We add this offset to the base address of the array and load the word from the location into T5, and that's where we do that. This index, the index in T0 is incremented and the jump sends the control. So the T0 is the index in T0 is incremented there, and after this the program executes this instruction which sends the control back to the instruction pointed out by this label, by the loop label. So at this point there is a branch equal instruction which makes a comparison between the index and the size and checks if the end of the array has been reached. If that is true and the index is actually equal to the size of the array, the execution jumps to the instruction pointed out by done. So basically if this T0 is equal to 2, the branch equal will jump there, exiting the loop. Otherwise the loop will continue executing in a similar fashion. Now removing this instruction, the jump instruction, actually makes this a simple if then else case. Now why is that? That's a question you should think about. Similar to the array example is the case of accessing strings. A string is simply an array of ASCII characters ending with a 0. In this example, we specify a string of alphabets, A to 0. Its data type is ASCIIs, which is used to specify a sequence of characters ending with a 0. Since each ASCII character is 1 byte long, we can think of a string as an array of bytes with the last character 0, and that is exactly what is shown in this conversion here. However, we need to be a bit careful about the endianness. The SPIM simulator simulates a little endian processor, so the order of the bytes inside the words are inverted, and that is what you can actually see here, but it might not be very clear from this example. But we will show this effect in the SPIM simulator in the next demo. To access each character in the string, we can use the load byte instruction, providing the correct offset along with the base address of the string. Since each character in the string is 1 byte, the offset for subsequent characters will increase by 1. Remember, in case of words in the array example, the offset always increased by 4, but that's not the case here. Here we are dealing with bytes, so it's always going to increment by 1. Now that brings us to a question. If you decide to access the string inside a loop and don't know the length of the string, how do you know when to stop?